Okay, we've got another moments and beam question here. It says, a contestant in a weightlifting competition is required to complete a barrel lift. A simplified diagram is shown below. So we've got a pivot point, and then we've got these three barrels lifted by the handles at this end by the contestant. We've got a free body diagram here, and showing the pivot point. You've got the three forces of the barrels, and you've got the force that's reaction to lift them, keep them in equilibrium. So nothing's moving, it's completely stationary. It says calculate the size of the lifting force F. Well, that's not actually that difficult. First of all, we know that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So everything stays in equilibrium. We also know that a moment is equal to a force times a distance. Okay, so what have we got? We've got 1, 2, 3 clockwise moments and just one anti-clockwise moment. So this one is equal to the sum of these three moments. So let's look at the moments. First of all, I've got 1600 newtons multiplied by the distance away from the pivot point, 0.8. You must add to that 1200 newtons multiplied by the distance away from the pivot point, 2 meters, not 1.2. You've got to go all the way back to the pivot point. Add to that 1000 newtons multiplied by the distance, 3 meters. And that is kept in equilibrium by our force, which is unknown, multiplied by the distance, 4 meters. Okay, let's just work these three out first. 1600 times 0.8 is 1280. 1200 times 2 is 2400. And 1000 times 3 is 3000. And that is equal to the force unknown times 4 meters. Now, to transpose the formula to get F on its own, we need to divide both sides by 4. These two cancel each other out, so we're left with F on its own. So let's just add these three together and divide it by 4. 1200, oh no, 1280 plus 2400 plus 3000 equals that, divided by 4 equals 1670, and the units, don't forget, newtons. Okay, describe two ways of reducing friction at the pivot point. Well, the friction point here needs to be reduced using lubrication. But you could also replace, this looks like a bush bearing, you could replace that with a roller bearing. Okay, over the page. It says, in order to set up some equipment, a winching system is used. Calculate the linear speed of the load. Well, here's the load being lifted by the winding drum, and the winding drum's being turned by a motor, and the motor is transferred through a worm and wheel. So we need to work out the speed as it reduces. So the first thing we need to do, a worm has only got one tooth, so we've already got a 50 tooth to 1 tooth reduction. So the way that we can show this is the 2000 RPM of the motor divided by 50 gives us the speed of the winding drum, which equals 40 RPM. Okay, now the rope is around the circumference, so we need to know the distance of the circumference. Then the diameter is given to us as 100. So circumference is equal to pi times diameter equals 3.14 times diameter 100, which equals 314 millimeters for 1 revolution. But we know that it's going at 40 revolutions per minute. So we need to now multiply this by 40 to give us the linear speed. 14 times 40 equals, that's 12,560 millimeters per minute. Okay, now we could turn that into meters per second, so that's 12.56 meters per minute, or 12.56 meters divided by 60 gives us 0.209 meters per second. Either of these answers are correct. State the name of the two parts of the mechanism that links the motor and the drum. Well, as I said already, this is a worm and that's a wheel. All we've got to do is get it the right way round. Part A is the wheel, part B is the worm. State the name of the mechanism that could be used to convert rotational to linear motion. Well, there are several, but one that I do know of is the pinion and the rack. Okay, so pinion and rack. I think you probably get away with a cam and follower as well there. Reciprocating into rotational, that's typical engine, and we're looking at a crank and slider. And that is another question finished.